In this video, I'm going to talk about the Lipchitz condition and the uniform convergence of Fourier series. So, although we have studied the convergence of Fourier series to itself, mathematicians are not satisfied by this. Mathematicians would like to study what kind of convergence will the Fourier series behave. And usually, one of the most common way to study the type of convergence is the uniform convergence. And in this video, I will first introduce what Lipchitz condition is and what kind of function will satisfy the Lipchitz condition. And in the next video, I'm going to prove that if a function satisfies Lipchitz condition, it indeed implies that the Fourier series converges uniformly. So let's state what the definition of Lipchitz condition is. F is said to satisfy Lipchitz condition on AB if there exists a constant L such that for all xy inside AB, the absolute value of fx minus fy is more than L times x minus y. Well, you may wonder, it is very similar to the definition of Lipschitz continuity. However, our L this time here is independent of the choice of x and y. And comparing this to Lipschitz continuity would depend on a point that we have chosen. And therefore, we know that Lipschitz condition is a stronger statement. And therefore, as we said that Lipschitz condition is a stronger statement to the Lipschitz continuity, and so we know that when f satisfies the Lipschitz condition on AB, f is immediately Lipschitz continuous everywhere on the interval AB. And by the definition of Lipschitz condition, it is kinda like a uniform Lipschitz continuity. As this condition is so important, we will investigate what kind of function will satisfy the Lipschitz condition. So the first kind of function that will satisfy the Lipschitz condition is called the C1 functions, which is the continuously differentiable functions. And the reason why it satisfies the Lipschitz condition is that from the fundamental theorem calculus, we know that the absolute value of fy minus fx is equal to the absolute value of the integral from x up to y of f prime z dz. And if we let m equal to the supremum of the absolute value of f prime x, where x lies inside AB, then we know that it is more than or equal to m times the absolute value of y minus x. And therefore, from the fundamental theorem calculus, we know that a C1 function indeed satisfies Lipschitz condition. The second type of function that will satisfy the Lipschitz condition is piecewise C1 function. So let's recall what the definition of a piecewise C1 function is. F is a piecewise C1 function if there exists a partition A0, A1, A2 up to AN of AB such that the restriction of F within AI-1 AI is a C1 function for I which lies inside the interval 1 up to n. And the reason why the piecewise C1 function is a function that satisfies the Lipschitz continuity, we consider xy that lies inside the interval a-1 ai. And we know that from the previous argument that as it is a C1 function inside this interval, we know that the absolute value of fx minus fy should be smaller than mi times x minus y, where mi is the supremum of absolute value of f prime x where x lies inside the interval ai minus 1, ai. And as there are finitely many mi here, and therefore if we choose L equal to the maximum of mi, where I lies inside the interval 1 up to n, then we are done. So this is the end of the video about the introduction of the Lipchitz condition, and in the next video I'm going to prove that Lipchitz condition implies that the Fourier series converges to f uniformly. See you in the next video.